Welcome to Chapter 4, where we conduct a rigorous quantitative comparison between composition-based features and GNN structure-based features. Using the MapBench benchmark, we'll evaluate random forest with MagPi features against CGCNN across multiple dimensions: prediction accuracy, statistical significance, computational cost, data requirements, and interpretability. By the end of this chapter, you'll understand the MapBench benchmark structure and evaluation protocol. Compare prediction accuracy of random forest and CGCNN with proper statistical testing. Measure and compare computational costs. Analyze data requirements using learning curves. Compare interpretability methods like SHAP values and attention mechanisms. And build a decision flowchart for practical method selection. Let's start by understanding the MapBench benchmark, which provides a standardized platform for evaluating machine learning models in materials science. MapBench is a standardized evaluation platform that defines multiple material property prediction tasks with pre-split training, validation, and test data. This enables fair comparison across different research studies. The standard evaluation protocol uses five-fold cross-validation. In this chapter, we focus on two large-scale tasks: formation energy prediction with over 130,000 samples and band gap prediction with over 100,000 samples. The main MapBench tasks vary in size and complexity. MapBench MPE form predicts formation energy on over 130,000 samples. MapBench MP gap predicts band gap on over 100,000 samples. Smaller tasks include perovskites at about 20,000 samples, phonons at over 1,000, and JDFT2D at a few hundred. All tasks use mean absolute error as the evaluation metric, enabling consistent comparison. Now, let's implement both methods on the MapBench benchmark for a fair comparison. The random forest implementation uses MagPi features. First, we take each crystal structure's composition MapMinner's element property is a composition featureizer, so the structure itself is discarded at this step, and pass that composition to the MagPi preset, which returns a 132-dimensional vector. Then, we train a random forest regressor with appropriate settings. Using five-fold cross-validation, we achieve good predictive performance. This provides our composition-based baseline. For CGCNN implementation, we convert each structure to PyTorch geometric data objects. Atoms become nodes with one-hot encoded atomic numbers, and edges use Gaussian expanded distances. We train a multi-layer CGCNN for sufficient epochs on each fold. The result is better predictive performance than random forest. Note that GPU acceleration significantly reduces training time. Comparing the two methods quantitatively, CGCNN achieves better MAE than random forest, with notable improvement. RMSE shows similar improvement. R-squared also improves with CGCNN, but we need to verify whether this difference is statistically significant or merely by chance. Statistical significance testing helps us determine whether the observed accuracy difference is real or could have occurred by chance. We use a paired t-test because both models are evaluated on the same 5 data splits. The null hypothesis is that the mean MAE difference between methods is 0. The test statistic t is calculated from the mean difference divided by its standard error. Our result shows a very high t statistic with an extremely small p-value, far below the conventional threshold. We can confidently reject the null hypothesis. The difference is statistically significant. The confidence interval for the MAE difference does not include 0, confirming statistical significance. In this worked example, Cohen's d comes out around 9, far above the conventional threshold of 0.8 for a large effect, though bear in mind these fold-level errors are illustrative figures, and real benchmark comparisons rarely produce an effect size anywhere near that big. This indicates not just statistical significance, but substantial practical importance. The improvement in accuracy is both real and meaningful. Beyond accuracy, computational cost is crucial for practical deployment. Let's compare training time, inference time, and memory usage. The computational cost comparison reveals significant differences. Training time is much faster for random forest versus CGCNN, about 40 times faster. Inference time is also much faster for random forest, over 10 times faster. Memory usage is lower for random forest, about 1/3. The key trade-off question: is the accuracy improvement worth the training time increase? This depends on your use case. Data efficiency analysis, using learning curves, helps us understand how much training data each method needs. Learning curves plot model performance against training data size. In the small data region with limited samples, random forest outperforms CGCNN because it's more data efficient. In the medium region, the methods compete closely. With large amounts of data, CGCNN clearly wins and continues improving. A key insight: random forest saturates early, while CGCNN keeps benefiting from more data. These insights lead to practical recommendations. With fewer than 10,000 samples, random forest is recommended for its data efficiency. With 10,000 to 50,000 samples, the choice depends on available computational resources. Above 50,000 samples, CGCNN is recommended for superior accuracy. A hybrid strategy often works well. Start with random forest for quick baseline, then migrate to CGCNN as data accumulates. Interpretability is essential for understanding predictions and building trust. Let's compare the interpretability approaches of each method. Random forest with SHAP values provides intuitive interpretability. SHAP, based on game-theoretic Shapley values, quantifies each feature's contribution to the prediction. For MAGPIE's many features, we can identify which elemental properties like electronegativity or atomic radius are most important. This composition-level interpretation is intuitive and easily explained to domain experts and stakeholders. CGCNN interpretability is more complex. Standard CGCNN lacks explicit attention mechanisms, though we can visualize layer activations. More advanced approaches include graph attention networks that learn attention weights, or GNN explainer for post-hoc interpretation. These provide structure-level insights showing which atoms and bonds are important. However, interpretation requires more domain knowledge. Comparing interpretability approaches. Random forest with SHAP targets feature importance at the composition level, with solid theoretical foundation in Shapley values and high intuitiveness. CGCNN methods target atom and bond importance at the structure level, based on neural network activations with moderate intuitiveness. Choose based on the insight granularity you need. Composition level for overall trends, structure level for specific interactions. Let's synthesize all our findings into a practical decision flowchart for method selection. The decision flowchart starts with data size evaluation. Less than 10,000 samples points to random forest. 10,000 to 50,000 requires checking GPU availability. With GPU, consider CGCNN. Without, stick to random forest. Above 50,000 samples, ask whether accuracy or speed is priority. Accuracy priority leads to CGCNN with statistical significance testing. Speed priority requires checking real-time requirements. The 5 key decision criteria are: first, evaluate training data size relative to the 10,000 and 50,000 thresholds. Second, confirm computational resources, especially GPU availability. Third, assess the accuracy versus speed trade-off for your use case. Fourth, verify statistical significance with proper testing. Fifth, determine interpretability requirements based on your audience and application. Let's summarize our findings across all evaluation dimensions. For accuracy, CGCNN achieves meaningful improvement. Statistically, the difference is highly significant. For training, CGCNN is about 40 times slower. For inference, CGCNN is over 10 times slower. For data requirements, use random forest below 10,000 samples and CGCNN above 50,000. For interpretability, use random forest plus SHAP for composition insights and CGCNN for structure insights. Practical recommendations follow 4 stages. In the exploratory analysis stage, quickly build a baseline with random forest and MagPy. In the accuracy improvement stage, introduce CGCNN if data exceeds 50,000 samples and GPU is available. In the production operation stage, make the final decision after evaluating the inference speed versus accuracy trade-off. Consider a hybrid strategy. Start with random forest initially, then migrate to CGCNN after accumulating sufficient data. In the next chapter, we'll explore hybrid approaches that combine the best of both worlds. We'll learn about early versus late fusion strategies for combining composition and structure features, examine architectures like ALIGNN and MEGNET that integrate multiple information sources, and understand when hybrid approaches outperform either method alone. See you in Chapter 5.